Hello everyone. In this lesson we will get to know several commonly used special diodes. The diodes we discussed previously were all applied based on their unidirectional conductivity. In fact, there are many diodes whose applications are based on other characteristics, such as Zener diodes, varicap diodes, photodiodes, and light-emitting diodes. We will focus mainly on the Zener diode, while the other types will be introduced briefly. The Zener diode, manufactured using special processes, can operate under reverse breakdown and will not undergo thermal breakdown within the specified current range. On the diode characteristic curve, this appears as a rapid increase in reverse current after reverse breakdown, with a very steep curve, indicating that when the current changes over a wide range, the voltage changes very little, showing excellent voltage regulation characteristics. Therefore, the Zener diode is also called a regulator diode. Parameters describing the voltage regulation characteristics of a Zener diode include the Zener voltage, the minimum operating current, and the maximum operating current during regulation. If the reverse current is less than the minimum current, the Zener diode will return to the cutoff state and regulation will no longer be possible. If the reverse current exceeds the maximum current, the diode may undergo thermal breakdown. The Zener voltage Vz is essentially the voltage corresponding to the test point Q. The negative Vz0 indicates that the reciprocal of the slope of the tangent through point Q intersecting the horizontal axis is the dynamic resistance of the Zener diode after breakdown. This resistance is directly related to the voltage regulation characteristics. The smaller the resistance, the better the regulation performance. From the tangent at point Q, we can write the equation Vz equals Vz0 plus Rziz. In the ideal case, Rz equals 0, meaning the characteristic curve becomes a vertical line, and when the current changes, the voltage remains constant. An ideal voltage regulation characteristic. To distinguish it from a regular diode, the Zener diode symbol has a small right-angle bend at the cathode. Its circuit model in reverse breakdown can be represented as shown in figure C. Since the Zener diode operates in reverse breakdown under normal use, its voltage and current reference directions in a circuit are opposite to those of a regular diode. That is, its reverse breakdown voltage and reverse current are both marked as positive values. In engineering applications, the effect of Rz is often ignored, assuming Rz is almost equal to 0, in which case Vz equals Vz0. Because of its voltage regulation capability, the Zener diode is widely used in DC voltage regulation circuits, and sometimes in signal processing circuits for clipping purposes. When building a voltage regulation circuit using a Zener diode, the first step is to ensure it is in reverse breakdown. That is, the supply voltage Vi must be greater than the Zener voltage Vz. Second, a current limiting resistor R must be connected in series to limit the current through the diode within the allowable range. Third, the load resistor is connected in parallel across the Zener diode, so the voltage across the load equals the Zener voltage. When the load resistance changes or the DC input voltage fluctuates, the Zener diode's regulation keeps the voltage across the load constant. When designing the specific parameters of this voltage regulation circuit, we must select an appropriate Zener diode based on the load voltage and current requirements, as well as the input voltage fluctuation range, and then calculate the current limiting resistor value. For example, if the input voltage fluctuation range is known, and the output voltage and maximum output current are specified, the selection criteria for the Zener diode are: first, the Zener voltage equals the output voltage. Second, considering that the load may be disconnected, the Zener's maximum operating current must be greater than the sum of the minimum operating current and the maximum output current. Third, the maximum power dissipation of the diode must be greater than the product of the Zener voltage and the sum of the minimum operating current and the maximum output current. Once the Zener diode is chosen, Its center voltage, maximum operating current, and minimum operating current are fixed. Next, we must determine the resistance and rated power of the current limiting resistor. From the circuit, we can write the expression for the current limiting resistor as the voltage across the resistor divided by the current through it. Assuming the Zener diode's dynamic resistance is 0, we must consider two worst-case scenarios. 1. When the input voltage drops to its minimum and the load current reaches its maximum, the current through the diode must not be less than the minimum operating current. This yields the maximum value of the current limiting resistor. 2. When the input voltage rises to its maximum and the load is open-circuited, the current through the diode must not exceed the maximum operating current. This yields the minimum value of the current limiting resistor. This determines the allowable range for the current limiting resistor, and it is also easy to calculate its rated power. Next, let's briefly introduce the other types of special diodes. First, the varicap diode. We already know that PN junctions have a capacitance effect, and the equivalent capacitance is related to the applied voltage. During manufacturing, measures are taken to emphasize this relationship in varicap diodes. Figure A shows the symbol of a varicap diode, and Figure B describes the relationship between equivalent capacitance and reverse voltage. Different models of varicap diodes have different maximum capacitance values, generally ranging from a few picofarads to several hundred picofarads. The ratio of the maximum to minimum capacitance is called the capacitance ratio. Currently, varicap diodes can have a capacitance ratio exceeding 20. Varicap diodes are widely used in high-frequency technology. For example, in a television's electronic tuner, the junction capacitance of the diode is changed by controlling the DC voltage, thereby altering the resonant frequency and enabling channel selection. The Schottky diode is made by forming a barrier at the junction between a metal and an N-type semiconductor, so it is sometimes called a metal semiconductor junction diode. Figure A shows its symbol. The differences between Schottky diodes and regular diodes are: 1. The capacitance effect is very small, and the operating speed is very high, making them especially suitable for high-frequency or switching applications. 2. The forward conduction threshold voltage and forward voltage drop are relatively small, as shown in Figure B. Photodiode. The photodiode, as its name suggests, is a diode that can convert light signals into electrical signals. Figure A shows its circuit symbol and Figure B shows its circuit model. Unlike regular diodes, its package is transparent, and light can generate more minority charge carriers. That is, the concentration of minority charge carriers depends on the light intensity. The reverse current of a diode in the reverse cutoff state is formed by minority charge carriers. Without illumination, the reverse cutoff characteristic curve of a photodiode is the same as that of a regular diode, close to the horizontal axis with very small current. When the light intensity is 200 lux, the minority charge carrier concentration increases, the reverse current increases, and the characteristic curve shifts downward. When the light intensity increases to 400 lux, the reverse current becomes even larger, and the curve shifts further downward. The typical sensitivity of a photodiode is about 0.1 microamperes per lux. Photodiodes can be used in light detection applications such as light-controlled switches. The light-emitting diode also has a transparent package. This is its circuit symbol. When forward current flows, the material of the diode can convert electrical energy into light energy and emit it. Light-emitting diodes come in many varieties and are widely used in signal transmission, large displays, lighting, and other fields. When used together with photodiodes, they can detect obstacles, such as detecting when an elevator door is about to close. If connected through an optical fiber, they can also transmit optical signals. In addition to photodiodes and light-emitting diodes, there are also maser diodes in solar cells, among other optoelectronic devices, all of which have wide applications. These are the common types of special diodes. That concludes today's lesson. Thank you for listening.